In this lesson, we're going to look at rhombuses, rectangles, and squares, which are special parallelograms. So all of these have the same qualities as parallelograms, but they also have some other special qualities. So we're going to go through the theorems that have to do with these particular quadrilaterals. So a parallelogram, notice that it starts as a parallelogram, so it has to be a parallelogram in order to be a rhombus. A parallelogram is a rhombus if and only if the diagonals are perpendicular. So here we have diagonals going from each opposite vertex, and those meet at a right angle, making them perpendicular. So a parallelogram is a rhombus if and only if diagonals are perpendicular. Theorem 612 says a parallelogram is a rhombus if and only if the diagonals bisect a pair of opposite angles. So the diagonal right here is bisecting this angle so that each side, each angle on each side of that diagonal is congruent because it is bisected. So both of those opposite angles are bisected by that diagonal. Theorem 613 says a parallelogram is a rectangle. So here we're moving to a rectangle. And again, it starts as a parallelogram already. So a parallelogram is a rectangle if and only if the diagonals are congruent. So that means that the length from one vertex to the opposite vertex, both of those are going to be the same. So both of these sets are going to be the same length. Now, it's already a parallelogram, so the diagonals already bisect each other, but that's a previous theorem. So the new part is that the diagonals are congruent. So the square corollary, which means that it takes things that came before it and makes it a little more specific, a square has to fit the conditions of both a rhombus and a rectangle. So in order to prove that something is a square, you would have to have that it is a rhombus and a rectangle. Once you have proved both of those things, it's automatically a square. So here are those theorems all together in our note form. So the first two, 611 and 612, have to do with a rhombus, and 613 has to do with a rectangle. So if you can match one of those stipulations for a rhombus and then that the diagonals are congruent, you can automatically say that it's a square. So one thing that we did not discuss is the definition of these things. So we can also use the definition to prove something. So the definition of a rhombus is an equilateral quadrilateral, which means that it has four congruent sides. And the definition of a rectangle is a equiangular quadrilateral. So if all of the angles are the same, which have to be 90 degrees, then it's a rectangle. So a square, the definition is that it is a regular quadrilateral, meaning that all of the angles and all of the sides are the same. So those can also be used, but those are from previous times. All right, so the first thing we're going to do is we're going to decide whether these statements are sometimes, always, or never true. So here, the first one says the diagonals of a rhombus bisect each other. And so we have to remember that a square is both a rhombus and a rectangle. So diagonals bisecting each other happens in a rectangle. So is there any time when a rhombus can also be a rectangle? And that's yes, but it's not all the time. So this one is going to be sometimes true. And so this is only true if it is a square. So a rhombus is a rectangle only when we're actually looking at a square. So a square is both a rhombus and a rectangle. All right, the next one says the opposite angles of a rectangle are supplementary. So the opposite angles of a rectangle are supplementary. So if we think about that rectangle, it's equiangular. And since the angle sum of a quadrilateral is 360 degrees, each angle is 90 degrees. So what I know is that each angle is 90 degrees. And if you think about the opposite angles, we want to know if they're supplementary. So if each angle is 90 degrees, then two of those angles is going to be 180 degrees, which means that they're supplementary, and that is always going to be true. So the angles of a rectangle are always 90 degrees. So if you add two of them together, they're always going to be supplementary. All right, the next thing says a rectangle is a square. And so this is always, sometimes, or never. So for this one, a rectangle, if we think about the definition, all of the angles are the same. And then from our new theorem, the diagonals are congruent. So that is only going to happen sometimes. And so in order to be a square, it also has to be a rhombus. So it has to be connected to a rhombus in order to be a square. So there's a saying like a square is a rectangle, but a rectangle isn't a square. So a square is always a rectangle, but a rectangle is not always a square. And so in order for that to be true, it has to meet those other qualifications as well. All right, in example 2, we have here that this quadrilateral GHIJ is a square. So it is a square. That means we need to think about all of the other things that it also fits under. So it's also a quadrilateral, and we would use that to get the angle sum if we needed it. It's a parallelogram, because all of these special shapes we're talking about today are special parallelograms. It is a rectangle and a rhombus. So a square fits all of these different things. We can use properties of any of these previous shapes to find these angles that we need. So the first thing we want to find is the length of JK. So that is part of a diagonal. So for JK, we can use properties of any of these shapes that we've used. So in a parallelogram, the diagonals bisect each other. So from that, I know that the measure of GK is the square root of 2. So based on that, I'm going to also know that KI is also the square root of 2. And then in a rectangle, our theorem today says that diagonals are congruent. So this whole diagonal GI is going to be congruent to the entire diagonal JH. And we know both sides of that because it was bisected based on being a parallelogram. So what that means is that all of these little pieces are going to be the same in a square or in a rectangle. So all of those little pieces are going to be the same. So based on that, we are able to find that JK, the length of JK, is the square root of 2. So now let's move on to the next thing we need to find. The next thing we need to find is the measure of angle JKI. So JKI is this angle right here, which is where two diagonals meet. And so I'm just listing things that I know. Something that is important for this one is a property of a rhombus. And our theorem today about rhombuses and their diagonals were that they are perpendicular and they bisect the angles of the parallelogram. So since in a rhombus, the diagonals are perpendicular, I know that the measure of angle JKI is going to be 90 degrees. All right, so we've got that one. Since it's 90 degrees, since it's perpendicular, I'm going to kind of change this to this little box. So even though it does not look perpendicular, since it said that it's a square, I know that it is. All right, the next thing we need to find is the measure of angle HIK. So HIK is this angle right here. And so another property of being a rhombus is that diagonals bisect the angles. So this angle here is going to be bisected. If that angle is 90 degrees, because it's marked here with this box, the entire angle HIJ is a right angle. It's 90 degrees. So this angle HIK is going to be half of that. So for that, I'm going to do 90 divided by 2, which says that this angle will be 45 degrees. All right, the last thing we need to figure out is the perimeter of triangle HIJ. So first, let's highlight what we're looking at. So HIJ is this triangle here. So we're going to have to look at some different things to figure out what we're working with. But first off, let's just focus in on this triangle. So I can figure out what this entire length based on the diagonal is by adding those together. So the square root of 2 plus the square root of 2. Our radicals work a lot like variables. So that's kind of like our what our variable would be. And there are 2 of them. So that entire length is 2 root 2. Then I also need to know what the measure of HI and JI are. So since this is a square, all of the sides are going to be the same length. And the length that I have for a side, GH, is 2. So that means that these sides are also going to be 2. So to figure out the perimeter of this triangle, I'm going to add all of those together. So 2 plus 2 plus 2 radical 2. And so now we're going to combine like terms. So whenever we're working with roots, again, they work and follow a lot of the same rules as variables. So this 2 right here is a coefficient. And coefficients can't combine with constants like these 2. So we're going to combine those 2 constants. And then this 2 root 2 is just going to stay the same as it was. So the perimeter of that triangle in exact form is 4 plus 2 root 2. You could always estimate that by putting it into a calculator, but you're only going to estimate if it tells you to round. If it doesn't tell you to round, put it in its exact form just like that. All right, so the next thing we're going to look at is identifying these special parallelograms based on ordered pairs. So if we have the coordinates of each of the vertices of a quadrilateral or a parallelogram, we're going to use this method to figure out what kind of parallelogram it is. So the first thing we're going to do is to identify the diagonals by joining the non-consecutive vertices. So here is the first set of ordered pairs I have here. PQRS is labeled. And to identify my diagonals, I just want to connect the non-consecutive vertices. So I'm going to connect P to R, and I'm going to connect S to Q. So those are my 2 diagonals. So PR and SQ are my diagonals. The next thing is I'm going to find the slope of each diagonal, and that's going to lead me to Theorem 611. So Theorem 611 said that in a rhombus, the diagonals are perpendicular. So if I get perpendicular lines, then that's going to make it a rhombus. So I'm going to use my slope formula, and I'm going to look for opposite and reciprocal slopes. So we're going to start off by looking at these 2 diagonals and finding the slope of each. So the first diagonal was PR, and the second diagonal was QS. So I'm going to find the slope of each of those. So I'm just going to say that this is point number 1 for the first diagonal, and this is point number 2, so that I can plug that into the slope formula. So the slope formula says y2, -3, minus the first y, which would be 1, over the x value of the second point, which is -2, minus the x value of the first point. So I'm going to simplify this down. -3 minus 1 is -4, and -2 minus 3 is -5. So in simplest form, those negatives are going to cancel each other out and leave me with 4 over 5. All right, so here is the slope of the first diagonal. And now I'm going to find the slope of the second diagonal. So if they are perpendicular, this is a rhombus. So for this one, I'm going to say that S is point number 1 and Q is point number 2. It doesn't matter as long as you keep the order matching. All right, so for my formula, the second y minus the first y over the second x minus the first x. All right, so whenever I simplify this, I have -4 over +5. All right, so if I look at these two slopes, they have opposite signs, but they're not reciprocals. So these two diagonals are not perpendicular, which means that this is not a rhombus. So since these are not perpendicular, this is not a rhombus. And if it's not a rhombus, it's not a square. So I know that it can't be a rhombus and it can't be a square. So now I'm going to check and see if it's a rectangle. So to figure out if it's a rectangle, I'm going to use theorem 613, which says that the lengths are congruent. Each diagonal is congruent in length. So we're going to use the distance formula, which is the first thing that's listed, or the Pythagorean theorem, where you think about each ordered pair and how far apart they are. So my personal preference is to use the Pythagorean theorem. And the way that I like to do it is by stacking the coordinates, or like putting them in a table. So I have 3, 1, and -2, -3. And so the A value and the B value that we find are the distance between those points. And it's always positive whenever we're looking at distance. We're just counting how far it is. So from 3 to -2, that's 5 units. And from 1 to -3, that's 4 units. So the length of this is going to be the square root of 5 squared plus 4 squared, which will be 25 plus 16. And that'll give me the square root of 41. So I don't have to put it into a calculator and reduce it. I just want to see if this other one gives me the square root of 41 as well. So for QS, now I'm going to plug in those coordinates to a table. So that's -2, 1, and 3, -3. And I'm going to look at those distances. So from -2 to 3, that is 5 units. And from 1 to -3, that's 4 units. So I can tell as I'm plugging this in that it's going to be the same because I'm plugging in the same numbers. So since those diagonals have the same length, that means that the diagonals are congruent. So PR is congruent to QS. So that means that this is a rectangle. So this parallelogram that was given to us is a rectangle. So we're going to classify it based on these things. If the diagonals are only congruent like they were here, that's going to be a rectangle. If the diagonals had been only perpendicular but not congruent, that would be a rhombus. If it had met both of the qualifications and was congruent and perpendicular, that would make a square. And if it failed both of the tests, it would be none. It would just be a parallelogram. So now let's repeat that with this next set. So we're going to identify those diagonals first. So the first diagonal is PR, and the second diagonal is QS. So it's the same letters as we used last time, but we just always go across the shape. So the first thing we did with those was we found the slope. So for the slope formula for P and R, I'm going to do 2 minus 2 over -3 minus 5. So that'll be 0 over -8, and we always reduce, so 0 on top makes a 0 slope. So in order to be perpendicular to this, I'm looking for an undefined slope. So I'm going to see if I get that whenever I find the slope of QS. So I'm going to do 9 minus -5 over 1 minus 1. So this will be 14 over 0. With the 0 on the bottom, this is undefined. So based on this, these two things are perpendicular, which means that this is a rhombus. So I know it's a rhombus. Now I need to check and see if it's also a rectangle. And if it matches that qualification as well, then it will be a square. But first we have to test it. So from this first thing, we did find out that it is a rhombus. Now we're going to find those lengths. So to find the lengths, I find the distance between my x values. So from 5 to -3, that is 8 units. And then from 2 to 2, that is 0 units. So this will be the square root of 8 squared, which remember, those are inverse operations. So if one of your numbers cancels out, it's just the length between the other two. So the length of PR is 8 units. And then I'm going to do the length of QS. So for QS, the distance between my X values is 0. So that tells me, I forgot to put the squared on that one. That tells me that that's not going to change anything. And then the distance between -5 and +9 is 14. So since I have a 0, I'm just going to take the other number. So since it's a 0, I just take the other number. This one's length is 14. So these are not congruent. So that means it's not a rectangle. But it was perpendicular. So this shape is a rhombus. So you're going to use those diagonals and find those distances and slopes to figure out